Hello, everyone, and welcome to this short lecture on convolution and reverb in the Web Audio API, where we'll be talking about reverberation, giving a very brief introduction to that, and the mathematical function convolution, which is often used for implementation of artificial reverberation, and show how this can be done within a web page using the Web Audio API. So, what is reverberation? Reverberation is essentially just a series of delayed and attenuated sound waves. When someone speaks in a room, their voice propagates in all directions, but is mainly directional, and it bounces off of the wall. It reaches walls, objects, ceiling, floor, and each time it gets attenuated when it interacts with that object and gets reflected back, much like billiards balls on a billiards table or pool table. So sound travels multiple paths from the sound source, someone speaking or playing a musical instrument, before it arrives at our ears and we hear it. There is the direct path, which is almost always the strongest and first path of the sound to reach your ears, direct from source to microphone. But there are also reflected paths, bouncing off of all of the objects in the room. They are attenuated, partly due to the extra distance that they travel, but also due to some sound being absorbed when it hits the wall. This gives us a sense of the spaciousness of a room. If your eyes are closed and you listen to sounds recorded in different rooms, you can get a sense of whether that room was a cathedral or a bathroom or any other type of room, especially those rooms that you're familiar with the type of reverb. You can get an idea of the size, the shape of the room, what might be in the room, whether it's soft surfaces or highly reflective surfaces. So it's a very powerful technique often used in sound design. What is the impulse response? Consider a pulse that has been filtered or transformed over time so that there are copies of that pulse known as delta functions, scaled copies of a pulse, which is a short signal just of a high amplitude. The copies will be attenuated over time. If one considers a situation where one pops a balloon or shoots a starter gun or claps their hands in a reverberant environment, what you hear is not just the single pulse, but you hear these reflections, and those are the reflections due to reverberation. So a figure like this, an impulse response, characterizes the room and gives you all the information that you need to understand reverberation in that environment for a given position for a source and a given position for the listener. In the plot shown here, each vertical line marks different copies of the sound. By the way, we're only showing absolute magnitude here, so in practice, the reflections could be positive or negative. But what to look at here is that it's comprised of early reflections and late reflections, where the early reflections have some gaps between them because there's quite distinct timing differences between the direct sound and the reflection off of the first wall, off of the next closest wall, and so on. But the rest of the response, all of these reflections blur together, and so it's more characterized by the shape, the envelope of this curve. So why do we add artificial reverberation to recorded sounds? There's lots of reasons, but basically we typically use what's known as close miking. It's a recording technique, a fairly simple to understand one, that boils down to putting the microphones close to the instrument that you are recording so that you can capture mostly the direct sound, so that there's less interference from other sources, less background noise picked up from the environment around. But you then need to compensate for this fact because this is not a natural listening environment. When one listens to a performance, one typically doesn't want to have one's ear right next to the musical instrument. And headphones have no natural reverberation. If you listen to music in a reverberant environment over headphones, you won't pick up all the natural aspects of that environment. So for all of those reasons, one might want to add natural reverb to a recording. And then, of course, one might want to add unnatural, unrealistic reverb to make something sound eerie, artificial in some sense. So, given that there are strong justifications for using reverb, given that the impulse response that characterizes reverb can be recorded, we can move on to look at how to do this as an audio effect using the Web Audio API. And this is done using convolution. The reverb can be fully characterized by its impulse response shown previously. Essentially, for a pulse as input, the recording would give values over time for that pulse. So you record a pulse, what you get out for an actual recording in a real environment is the impulse response. If we have that, we might have recorded it using popping a balloon, and there's various techniques that, various different techniques that can do it even more accurately. We then apply reverberation by convolving the signal with this impulse response. Convolution is a mathematical operation. Given here, the convolution of two signals, f, or two functions, f and g, as a function of a sample number n, is done by looking at all samples over all time and multiplying f by g as time reversed n minus m. So this is the value for the output n. Notice that although this has to be done over all time, if one deals with finite length functions, so where there's zero everywhere except over a short interval, then the convolution is not in practice over all time. What does this actually do? Well, you can find a few animations online, and I recommend the wiki page on convolution is very good, but there's loads of resources. But it has this sort of behavior. If you consider two signals, a blue one and a red one, then imagine shifting one of the two signals over the other signal. The area under that curve is what results. And so this black line here, that is the convolution of the two signals together. One of the signals, you can consider it as sort of smearing out or spreading out the other signal here. In this case, the signals are a pulse of a quite large duration and then an exponentially decaying plot. So, in order to do this, there is one audio node that is important, but this audio node introduces some concepts we haven't seen before. There is an audio node that performs convolution, and it convolves an input signal with an audio buffer. We haven't yet dealt with audio buffers, but we will now. It's used to achieve a reverb effect. It can be used for many other purposes, but in the Web Audio API documentation, they assume quite rightly that one of the most common uses will be for reverberation. The node itself, as it's written, it has exactly one input and one output, but it also has properties. So like the oscillator node will have a property for frequency, the gain node for the gain parameter. Here we have a buffer, which is a one-channel or mono, two-channel or stereo, or four-channel audio buffer that we use to contain an impulse response used by the convolver node. It also has normalization, which simply normalizes this buffer so that it's to high amplitude. And this is done because people might use the convolution with many different recorded impulse responses. The impulse responses can all be recorded with different amplitude pulses, different microphones, and so in order to have them roughly equal loudness, they can be normalized. The default value here is true, and well, in my programming, I've never had reason to change the normalize to a false value. So we're going to demonstrate this convolution for a short pulse convolved with a simple impulse response. So this pulse is actually going to be a bit like a square wave type signal. But we'll look at that in a second. But first, note with the convolver here that convolver looks like two input functions. And so one would think two input signals, F and G. But because of the way convolution is typically implemented for dealing with impulse responses, it is phrased a bit differently. So it has the one input as mentioned. That is going to be our audio signal that we want to apply reverb to. And then the buffer is the stored impulse response that determines the reverb which will be applied. So the buffer here is one of the two functions. And convolution is commutative, so it doesn't matter if it's F convolved with G or G convolved with F. It always has that one input, which is the audio signal. Here I've shown it as G. The buffer, which is the impulse response. Here I showed it as F. And then the output is the result of convolution. So we need to set up an audio buffer in order to apply convolution. And that is a few lines of code all by itself. Regardless of the fact that we're going to use what is stored in this buffer for convolution, you need to use another aspect of the Web Audio API. And here we are using create buffer. Now, the buffer information could come straight from an audio file, so a WAV file or something like that. But in this case, we're just creating raw data. So the data still needs to have a sample rate to go along with it. So we know how long in time the samples correspond to. Once we have this audio buffer, the audio can be played by passing it to an audio buffer source node. In this case, though, we're not going to play out this audio buffer. We're going to use it for convolution. And the audio buffer is typically a short file, so less than 45 seconds, often much, much less. For the case of reverb, 1, 2, 3 seconds are typical values. The buffer is going to contain audio data, so all of the values will be between -1 and 1. Here we just have one channel, so an array of values between -1 and 1. So let's go ahead and create it. This function down here takes as input a duration and a decay rate and creates something that looks like an impulse response. To jump back, and keep in mind here, I'm just showing absolute magnitude, so the values would be positive or negative, but we've ignored the exact behavior of the early reflections and instead are just trying to capture some sort of decay rate going on here, down to a certain time where, for all purposes, it's about 0. That's what's given by this function here. Let's walk through this step by step. We're going to create an impulse response. If we know it is, say, 1 second long, then the length will be given by the sample rate, samples per second, times 1 second. Gives you the length in samples of this impulse response. And so we can create our buffer. We call it the impulse here. Which is, which takes a few parameters. It's going to have one channel, the number of samples given by length, and the sample rate, which is the same as the sample rate for our audio context. Then we say that the impulse response, so what we're going to store in this buffer, is going to be just a single channel. It's going to be the data that we'll store in this first channel of the buffer. And this data is going to be random values. So this will produce random values between +1 and -1 that have an envelope such that they decay towards 0. And the decay value here determines that decay rate. If the decay was set to 0, then we'd just be multiplying these values by 1, and so we'd simply have a random number generator. If the decay value is 1, then what we're basically doing here is having the values linearly decay over the whole duration from 1 to 0. But as long as the decay is greater than 1, then it decays exponentially. So for instance, if there were just 10 values, you would multiply the first value by 1, then the next by 0.9 to the power of whatever the decay rate is, then 0.8, then 0.7, then 0.6. And then we return this impulse that we've created, which is a buffer which stores those values in one channel. But that's not it. That's just creating the buffer that the convolver node will use. So now we actually have to work with the convolver node. We're going to create a short periodic pulse. I will make one correction to the code right here, which I saw a mistake. I think playing around with things, I changed it from a sawtooth to a sine wave in the code, but didn't change it in this copy of the code. So we're going to create this short sinusoidal pulse of 1/10 of a second, or 100 milliseconds, and we are going to apply the convolver to this pulse. In order to create a pulse only of 100 milliseconds, we create an oscillator node and we connect that to a gain, and then at a given time, 100 milliseconds, we have the gain node's gain parameter jump to 0. So it cuts off this oscillator after 100 milliseconds. We create the impulse response as our audio buffer that we'll use, using what was shown previously. And we set the impulse response as the buffer parameter value for the convolver. So, we created our source here. Remember, to start the source, we need to start sources like oscillator nodes or constant sources. And we create our gain node, call it amplitude, have that cut off after about 1 second. And we then call the impulse response function from the previous slide, set it to 1 second, with an exponential decay. I might have changed this in the code just to make the audio a bit more pronounced while doing the video, but you'll see that in a second. And now we create a new convolver node and give it a buffer parameter of this impulse. So we can now do the connections, the heart of what goes on in the Web Audio API. The source goes to the amplitude connects to the convolver then goes to the output, the destination for this audio context. Let's have a listen. Or, better yet, let's look at the code. Here's the code that was just being discussed. There's the impulse response function. Here is the code, virtual copy and paste. I think I've set it for only 1 second of impulse, and decay value of 2, decay value of 1. Let's exaggerate this a little bit, make it 3-second impulse response. So a quite significant amount of reverb here, and let's listen. So you should have heard quite an echoey sound there. Let's go ahead and compare that with what this sounds like without any reverberation, because you always want to know that the sound you are producing is the sound that you meant to produce. Here, we connected the source to the gain control amplitude, and rather than that then going through a convolver, we want that to go directly to the output. So source connects to amplitude, amplitude then connects to the destination. Let's hear this.